All right, well, let me get started. So I want to start with some motivation of what we're doing. So let's imagine that you have a sequence of values, and we want to be able to do two operations. One is we want to be able to update any value to a new value. And the other operation we want to be able to do is a range query, where we want to be able to get the sum of an arbitrary contiguous subsequence of values. And so the question is how to be able to do arbitrary interleavings of these two operations in an efficient way. And so one thing we could do is just store the sequence in a mutable array. And of course, updates are very fast, but doing a range query, you just have to brute force add everything up. And another thing we could do, if you try to be a little more clever, and we could say, well, why don't we cache prefix sums? So if pi is the sum of all the values up to ai, right, then we can do a range query by just subtracting the sum of everything up through j, and then subtracting the sum of all the things up to I-1. And that means that range query is now very fast because it's just two constant time lookups, but update is slow because now to update something you have to update all of the cached prefix sums, all of it. Okay, so there are two nice solutions to this problem that give us log time updates and range queries. And segment trees are very easy to understand. And Fenwick trees are extremely fast, but harder to understand. And so I want to tell you about segment trees first, and then explain how we can understand Fenwick trees as sort of an optimization of segment trees, which is not how they're usually presented. All right, so what is a segment tree? So on the bottom here we have our sequence of values, and we just build a full binary tree on top of it, where each node stores the sum of the nodes below it. Okay, and so of course the root is the sum of the entire thing, and so on. So to do an update, we only have to update the cached sums on the path from the node we updated to the root, and so that takes log time. To do range queries, well, if we focus on doing prefix queries, we are essentially doing kind of a binary search for the end of the range that we want, and we can add up. We don't have to recurse all the way down to the leaves, right? We can add up these cached nodes as we go, and so that takes log time as well. And then, of course, if we can do a prefix query, we can do an arbitrary range query by subtracting. Okay, so this is very nice. For this was doing like arithmetic coding, where you're keeping track of frequencies of symbols that you've seen, and you need to be able to quickly query and see sort of cumulative frequencies for things. And apparently also there was a paper published in 1989 which had the same idea by Boris Ryabko, but I don't read Russian, so I don't know actually what's in that paper. So let me show you, this is a typical imperative implementation of Fenwick trees. And I do not expect you to understand this code, and that is the point. I do want to point out a few things about it, though. So you can tell that whatever this is doing, it looks like it's going to be pretty fast. We're just storing an array. We're not storing tree nodes with pointers and such. You can see that there's this range operation down near the bottom that subtracts prefix things. That looks familiar. But then the prefix function and the update function are both, they have these little loops which involve adding or subtracting something called LSB. And LSB is defined as the bitwise AND of I with negative I. And so what the heck is that doing? And what does this have to do with range sums and all that stuff? So the goal for the rest of this is just to kind of explain where this comes from. This is an ahistorical, I don't think Peter Fenwick came up with it in this way, but it's one way we can understand these. Okay, So let's think about segment trees again. So back to a full binary tree with these cached sums, and it turns out that we actually don't need a bunch of these values. And so if we just, I've grayed out some of the values. So in particular, every node that is a right child, I have grayed out, and we don't need those. So you can convince yourself that it would be possible to reconstruct the values in all the grayed out nodes. So for example, the little square all the way in the bottom left underneath the 4, since 4 has to be the sum of 0 and whatever's in that gray square, right? We know that there has to be a 4 there, and so on. You could fill in all the rest if you wanted. But we don't need to reconstruct those grayed out values. We can just do updates and range prefix queries using the existing values. So updates are easy. You just ignore the grayed out nodes. You don't need to update them. And prefix queries, it turns out we're only using the non-grayed out nodes anyway. I won't prove that for you right now, but you can convince yourself that the nodes that actually, whose values get used are the ones that still exist. And so looking at this, it then occurs that since every right child is grayed out, we can sort of imagine every node sliding all the way down into the right until it lands in that array. And then we can actually store all the values in this tree in this array. So it's an array that's the same size as our original sequence, only every other value is actually an original value from our sequence, and the other ones are sort of these cached sums. And this is exactly what is called a Fenwick tree. And you usually see it, if you look up explanations of it online, you'll usually see it presented like this, drawn as a tree, but sort of in a right-leaning style, so that each node is kind of exists above the place in the array where it's actually stored. Okay, but the big question is, how do we move around in this tree? And when I say move around, what do I mean? So, for example, let's say that we wanted to update, the number 1, the first 1 on the very bottom, and so we need to go up and update. Its parent is, well, it has a grayed out parent. But if we keep going, we need to update. Update the 7, which is the parent of the 6, right? And then the parent of 7 is 22, and that's stored, somewhere else in the array. How do we know where different things are stored relative to each other? So that's the big question. So, okay, to answer this, let's go back to thinking about full binary trees. So there's a really nice way to number full binary trees that you've probably seen before. You can put 1 at the root, and just keep numbering them consecutively. Right, and this has the nice property that each, the children of a node are numbered, are twice its value and twice plus 1. So, the 2 has children 4 and 5, so that's twice 2 is 4, and twice 2 plus 1 is 5, and so on. This has the property that, right, every right child is odd, except the root is a weird special case because it's odd, but it's not a right child. And so we're just going to switch to using 2 for the root. Now this means the numbers are no longer consecutive. Like 3 is missing, 6 and 7 are missing, but we don't really care about that. It still has this nice property that every node, its children are twice it and twice plus 1, and all the nodes on a particular level are just numbered consecutively, like 8, 9, 10, 11, and so on. Okay, so. And of course, in binary, this looks really nice because to move down from a root, or from any node, you either add a 0 or a 1 to the end of the binary representation, and to move up from a node to its parent, you just do a right bit shift. So that's so. The point is, moving around in a tree numbered like this is very easy, right? We know to move up, we just do right bit shifts, move down, we shift in bits, and so on. So here's the plan. If we can figure out how to convert between this numbering scheme that I just showed with a full binary tree and the indices in a Fenwick tree array, then we can move around a Fenwick tree by saying, well, let's first convert to a full binary tree index, do whatever moving around we want in the tree, and then convert back. And then hopefully we can fuse these operations together to get some kind of nice way to directly compute moving around in the Fenwick tree. So in order to do that, we want some kind of domain-specific language for manipulating numbers in binary. So this is using Haskell notation. It's not really specific to Haskell, but we can make a data type for bits. We can have not, and, or standard kind of things. And then we're going to represent binary numbers using 2's complement, which probably many of you are familiar with. But the basic idea is, so here we're counting down in binary, 5, 4, 3, 2, 1, 0. And if we imagine what would happen if you kept going, if you imagine the bits as like an odometer, if you keep counting down past 0, it kind of all rolls over to 1. All rolls over to 1s. And so we're going to use this infinite stream of 1 to represent -1. And you could keep counting down, right? You would get infinite stream of 1s and then 0, that's -2, and so on. So we want to represent such infinite streams of bits. And in Haskell, we could use an infinite lazy list, except this is really not a good idea. So we don't have decidable equality for these things. We can't convert from an infinite list of bits to a number because you never know when to stop. There could always be more bits that you need to look at. And it allows junk values, like, something that alternates infinitely between 0 and 1 is not a valid 2's complement number, but that would be a valid list, so we don't want that. So instead we're going to use representation where we have an explicit constructor to represent infinite repetition. So basically every number has to eventually end with all 0s or all 1s. And so we'll have a constructor for that, and then a SNOC constructor. I'm hiding some details here under the rug, and you can see the paper for the actual details of how this works. And then we can encode some kind of standard operations on bits, like and, increment, invert. Negation in 2's complement is just you invert all the bits and then you increment. And if you have never seen that, you can work that out for yourself. It's cute how that works. But so we saw this LSB thing in the Java code that I showed you, and LSB stands for least significant bit. And so the idea is, well, if you see a 1 bit at the end of a number, then we just say, well, the number with the least significant bit is that 1, and so we'll just return all 0s and a 1. If we have a number that ends with a 0, we just kind of keep looking recursively for where that last bit happens. And we just have a case for all 0s just so it's total. And right, and so we saw in the Java code there was this LSB function that did a bitwise AND of I and -I. And it turns out that we now have enough in our little DSL to prove that indeed LSB of x is equal to the bitwise AND of x with its negation. And this is an easy proof by induction. There's some other things in the DSL, like setting and clearing bits, testing bits, left and right shifts, and then this sort of generic while combinator that just keeps applying a function as long as a predicate is true. And there's various lemmas about how these things interact. We can rewrite them in various ways. Okay, so how do we convert between indices in a Fenwick array and indices in a full binary tree? So I'm going to go through this pretty quickly. There, you can look in the paper for more details, but so here's sort of, on the top, the blue numbers are Fenwick array indices, just numbered 1 through 8, and then the other numbers underneath are the corresponding full binary tree indices. If we go one more level, we can see that these numbers we had here, 16, 8, 18, 4, 20, they show up, these green numbers are the same. They're interleaved with some other ones. And we can kind of see why that happens, because we keep the same structure of the tree. When we add one more level, we sort of end up interleaving these new even values with the values that already existed. And so we can write a sort of interleaving operation on lists, and then define the sequence of values that we want inductively, right? So we start out with the base case of just 2, and then we interleave these consecutive even values starting at some power of 2 with the values from the previous layer. And so we end up with this conversion function that says, well, if you have an index in a Fenwick array and you want to convert it to an index in the binary tree, depends on whether k is even or odd, right? You either get something from the previous layer, so we have this recursive call, or right, something from this last layer looks like, this power of 2 plus, something dependent on k. And if we stare at this and we say, well, what is this doing? So it's as long as k is even, we're going to keep dividing it by 2. That is doing a right bit shift. And if k is odd, we're going to add this big power of 2 and decrement. So we can actually encode this in our little DSL for bit strings by saying, well, we're gonna set that 2 to the n plus 1. We're gonna set that bit. We'll set it first, and it'll kind of come along for the ride while we do some shifts. And then as long as the number is even, we shift right. And then finally, once we hit an odd number, we'll do that final decrement. And you can similarly derive the inverse operation to convert back. And then if you think about what do we have to do an update, the idea is, right, we want to find the closest parent that is still active, that is not grayed out. And the way we do that is, well, you would move up one level to get to the immediate parent, but then that might be grayed out, so you just have to keep moving up until you reach something that is not grayed out. And so to move up one level, we do a right shift, and then you keep moving up as long as you are at an odd node, that is, as long as you're at an inactive grayed out node. And then we just sandwich between, convert from Fenwick to binary and do this, and then convert back, right? So this is the function that would tell us how to move in a Fenwick tree from a node to its nearest parent that is not grayed out. And we could do a whole bunch of inlining things and rewriting using various lemmas and stuff. And we end up with something that looks like this. It basically says, well, you first set this pretty large bit, then you right shift, you shift out zeros, and then as soon as you're a 1 in the final place, you increment, and then you shift left again until that 1 that you set was back in the same place, and then you unset it. And essentially what this is doing, right, it's finding the smallest, it's finding the rightmost 1 and incrementing at that place. And this sort of sentinel bit is just sort of set to make sure that we can move things back to where they were before. And so you can prove, and there's a proof of this in the paper, that indeed this actually does correspond to taking a number and adding its least significant bit. And which is exactly what we saw in that Java code, right? It was saying, we'll start at some index I, and then each iteration, we're going to add its least significant bit to itself, and that will get us up to the next parent we need to update, and then we just keep doing that all the way up to the root. So there's more stuff in the paper. There's there's more pictures. There's actually proofs of all these things. I also talk about deriving this prefix operation, which was the thing that involved subtracting the least significant bit instead of adding. Thank you very much.
Okay, Brent, can you hear me?
Okay, Brent, can you hear me? Yes, I can.
Okay, I don't know if you were able to see the talks earlier in the session, but there's definitely been a theme of taking data structures and algorithms that were developed in the imperative world, bringing them into the functional. And one of the takeaways from a previous talk was, don't use indices, use cursors or zippers or something. I forget the exact word. But I'm wondering if you can imagine a version of what you're doing, because you've leaned really heavily into this, bits and twos complement. Is there a version that sort of makes the structure of the tree play a more central role in it and is able to move away from bits?
Yeah, that's a really interesting question. My original goal was certainly there's this existing imperative code that does this bit manipulation, and I wanted to explain where that comes from. But could you make a version of it that maybe does sort of a similar things but works in a more nicely functional way? Yeah, very possibly. I'll have to think more about that.
Great. We've got another question.
Hey everyone, this is Simon. Simon PJ. So often with these algorithm things, once you pick the particular API you want, and then you can say, well, in the literature, there's, somebody's done this particular piece of work that for that API, you can get this data structure, and then you can, as it were, rationally reconstruct it as you've done. But that doesn't feel very systematic somehow. It's a bit like sort of points in space. If you were to add, I don't know, concatenation to these trees or range deletion or something, then would it mean we tear everything up and start again? Or could you imagine, I don't know, just having a more systematic way to construct these kind of data structures, in the systematic way that you described, but yeah, with different APIs?
Right. Yeah, that's a really, really good question, and I don't know. But yeah, you're right. There is this feeling of, each thing is sort of this completely ad hoc solution to a specific set of constraints. Yeah, that's a really cool question. I don't know the answer to that.
So it's interesting because, you and Chris Okazaki, I would say you're the two people in the world probably who know most about this. So I guess this is for everyone else. Is a fertile area for PhD students, I think.
Yeah, right.
All right. Thank you, Brent. Let's thank Brent again.